In this segment, we're going to dig a little deeper into the independence assumptions of PCFGs and what that means in practice. So the symbols of a PCFG define the independence assumption. So if we have a pair of rules like this, S goes to noun phrase, verb phrase, noun phrase goes to determine a noun, when you're expanding here, the only thing you know is that you've got a noun phrase and you've got probabilities for how it expands. So the right way to think of categories in a PCFG is that they're kind of choke points for information flow. So we have the outside tree up here, and when we're expanding this noun phrase, we know nothing about the outside tree. All we know is that we're expanding a noun phrase. Or, looked at from reverse, when we're working out what paths to choose up here, we don't know anything about what went on down here. All we know is that this is a noun phrase over some number of words, and then we need to work out what happens above it. So precisely, this is a point at which there's an independence assumption. The assumption is you can work out the probabilities of things inside here, knowing only that this is a noun phrase, and you can work out the probabilities of things up here, knowing only that this is a noun phrase. That's a very strong independence assumption. And we can see clearly that it's too strong by looking at various cases. Here's one example. So if we just say, what are the chances of expanding a noun phrase overall? Well, the chance of a noun phrase expanding as a noun phrase, prepositional phrase in the Penn tree bank, it's about 11%. And the chances of it expanding as a pronoun, so this is something like a noun phrase goes to the pronouns she, that's 6%. And these are just the overall statistics. But let's suppose we now ask about particular categories. Suppose we know that this is a noun phrase under an S, so that's the subject noun phrase of a sentence. Then we find out the statistics are enormously different. So the chance of it expanding as an NPPP go down a little. But what's really dramatic is that the chances of it becoming a pronoun go up enormously, about 3.5 times. In contrast, if we know it's a noun phrase under a verb phrase, the chance of it being a pronoun drops, but the chances of it being an NPPP go up a lot. They more than double. Now, if you have a bit more background in linguistics, you'd say at this moment, well, of course, that's exactly what you'd expect based on knowledge about information structure of language, so that subjects are normally used for topics, established discourse reference, and therefore it's highly appropriate for that to be a pronoun, whereas inside the verb phrase, what you're normally doing is introducing new information, which therefore needs to be explained a little bit more, and therefore it'd be quite common for that to be a noun phrase with a prepositional phrase hanging off it, because that's one of the ways in which you can express more information. So you can say something like the man by the railroad tracks or something like that, where you're giving more descriptive content. But just thinking about it at the moment for our PCFG, well, what we're finding is that if we just say we're expanding a noun phrase, we're losing this additional information, which would let us give much better probabilities about how to expand it. Another way that you can see that your independence assumptions are too strong is when you run a basic PCFG and you find that it just does the wrong thing. So it's choosing rules that look wrong and it shouldn't have used, but somehow it's choosing to use them. Here's an example of this. So for a noun phrase like big board composite trading, the noun phrase structure that you're meant to choose in the Penn tree bank is just this flat structure. In general, the Penn tree bank uses a lot of flat structures for compound nouns like this. But if you train up a simple PCFG and run it on this sentence, the structure that you actually get is this one here, where it's put in an extra noun phrase node around big board. Well, it just shouldn't have done that, and your first reaction is, well, why did it do that? Because all of the compound nouns in the Penn tree bank have this kind of flat structure. Why didn't it learn that? But the reason that it was able to do this is that there's a different structure in the Penn tree bank where you do get these NP nodes at the start of an NP. And when that happens is with possessives. So here we have this possessive NP, and then you do have a noun phrase up here going to noun phrase, adjective, noun. And so what you'd like to say is, well, this rule here, it's okay to use it as for possessives, but this noun phrase isn't a possessive. But then that's precisely where the problem is, because both of these nodes are just marked noun phrase, and so we're not recording the information that this one here is a possessive noun phrase. So somehow we want to get more information into this category to say this is a possessive noun phrase. So the parser would know that you can't use that expansion rule when you have a non-possessive noun phrase like big board. So that's what we want to do. So we can relax the independence assumptions of a PCFG by encoding more information into the non-terminal symbols, a process that's often referred to as state splitting. So one of the first proposals for state splitting and showing how successful it was Mark Johnson noticed that you could improve a probabilistic context-free grammar quite a lot by encoding as part of each non-terminal also what was the parent category. And remember, you also saw this idea in the conditioning of the Charniak parser in a preceding segment. So Johnson's observation was that if you did nothing more but changed all of the non-terminals to also record in them what the parent non-terminal is, so you then effectively have a number of non-terminals squared space of non-terminals, that change alone, if you just train a PCFG in the regular manner, makes a big difference. It pushes up to your parsing numbers by a couple of %. So that's a useful idea, but there are other things that we might want to do that have a slightly different character. So for the example from the previous slide, if we want to rule out the big board bad pars, it seems like what we also want to do is know about possessive noun phrases. So possessive noun phrases are these ones like fidelities with an apostrophe S at the end, and they have a very different nature to regular noun phrases, but it wasn't being recorded in the category symbol. They're just being called noun phrase. So why don't we do state splitting and say, oh no, we're going to split out noun phrases that are possessives and call them an NP-pos, and then that information will also be captured in the grammar, and again we'll have a more accurate PCFG. Of course, there's a danger of doing this too much, and that is that if we have too much state splitting, we start getting more and more non-terminals, and our information about the non-terminals becomes sparser and sparser. And in particular, in the model we're going to show in the next segment, there was absolutely no smoothing of the rule rewrite probabilities. And so if you did too much state splitting, you'd end up having 0 probabilities from things that you haven't seen before. But unlike with word probabilities, where you basically have to smooth them, you can do a reasonable amount of state splitting of categories in this sort of a way before you have to deal with smoothing. And so what we're going to look at is, well, which ways of splitting categories are most useful for capturing probabilistic dependence that's needed to do a good job in PCFG parsing. Okay, I hope that gives you a more concrete sense about PCFG independence assumptions and how they can hurt you, but also how to solve them.